All right, let's jump right into this. We're going to tackle a really fascinating mathematical puzzle today. It's one of those things that looks so simple on the surface, but it actually peels back a layer on how math really describes our world. And it all kicks off with just one single line of text.
So here it is. This is our source, the clue at the heart of our whole puzzle. We've got two vectors, A and B. But notice anything? They're exactly the same, which means our puzzle is really about a much simpler question. What happens when you multiply something by itself?
And right now, you're probably thinking, wait, I know how to do this. 5 times 5 is 25, right? X times x, that's x squared. Easy. But here's the twist. With vectors, it's not that simple at all. In fact, you don't get one answer, you can get two totally different answers. So here's our game plan. First, we'll look at the puzzle. Then we'll break down what these vectors really are. After that, we'll explore the two ways to multiply them, actually solve our example, and then, the big finale, figure out why we get such different results. So this is the core of the problem. When you're dealing with vectors, just saying multiply isn't good enough. It's too vague. You have to be more specific. You have to ask, how are we multiplying? Because depending on how you do it, you get a completely different outcome.
Okay, so before we can even think about multiplying anything, let's make sure we're all on the same page. What exactly is a vector? You know, the best way to picture a vector is just an arrow floating in space. It's not just a number, like 5 or 10. It has two key parts. How long it is, that's its magnitude, and which way it's pointing, that's its direction. You need both. So what's up with those letters, the I, J, and K? Well, they're super important. They're called unit vectors, and you can think of them like the fundamental ingredients for moving around in 3D space. I is basically take one step east, J is take one step north, and K is take one step up. So when we look at our vector A, it's really just a set of instructions, like a treasure map. It's saying from wherever you start, go one step in the I direction, then 2 steps in the J direction, and finally 3 steps in the K direction. Boom, you've arrived. All right, now we know what we're working with. Let's get into the first way we can multiply this vector. It's called the scalar product, but you'll probably hear it called the dot product most of the time. And the most important clue here is in the name itself, scalar. A scalar is just a number, a plain old number with no direction attached. So when you do a dot product, you're not getting another arrow. You're just getting one single value. So what's this number telling us? In a nutshell, it's all about alignment. Think about it like this. Imagine you have two vectors and a flashlight shining down from above. The dot product is like asking, how much of a shadow does the first vector cast on the second one? The more they're pointing in the same direction, the bigger that shadow is going to be. Okay, so take everything we just said about the dot product and get ready for something completely different. This is method number 2, the vector product, also known as the cross product. And trust me, it's a whole different ballgame. So what's the big deal? Well, unlike the dot product, the cross product doesn't give you a number. It gives you something else entirely, a brand new vector, a new arrow with its very own length and its very own direction. So where does this new vector point? It's pretty cool, actually. It points in a direction that's perfectly perpendicular to the two vectors you started with, at a perfect 90-degree angle. Here's a great way to picture it. If your first two vectors are like two pencils lying flat on a table, their cross product is a new pencil pointing straight up at the ceiling. And how long is that new pencil? Its length is connected to the area of the little shape those two pencils on the table make. Okay, theory time is over. We've got our two methods, the dot product and the cross product. It's time to go back to our original puzzle, back to vector A, and see what happens when we actually do the math. This is where the magic happens. But wait, before I show you the answers, let's just do a quick side-by-side. Dot product, it's all about alignment, and the answer is a single number. Cross product, it's all about creating something perpendicular. The technical term is orthogonality, and the answer is a whole new vector. Got it? Good. All right, here we go. First up, the scalar product. We're going to dot vector A with itself. The question we're really asking is, how aligned is vector A with vector A? The answer is 14. Just 14. Not a vector, not 0. Hold that thought. Now for the other way of multiplying. What happens when we take the vector product? What happens when we cross A with itself? Now we're asking a totally different question. Give me a new vector that's perpendicular to both A and A.
And the answer is 0. A big, fat 0. Not a vector pointing off into space, but the 0 vector. Let's finally unravel this mystery. Because understanding why these results are so different, well, that's the whole point of this. So, why was the dot product 14? It's actually pretty straightforward. Remember, the dot product is all about alignment, about that shadow. And, well, nothing is more aligned with something than itself. You're getting the absolute maximum shadow possible, which mathematically just turns out to be the vector's length squared. Okay, but why was the cross product 0? This part is just beautiful. The length of that new vector from a cross product depends on the area that the first two vectors create. But think about it. What kind of area do two identical vectors make? They just lie right on top of each other. They form a line, not a plane. There's literally 0 area between them. So, if the area is 0, the length of that new perpendicular vector has to be 0 too. So what's the big takeaway here? It's that there wasn't just one right answer to what's A times A. The answer completely depended on the question we were asking. When we asked about alignment, we got 14. When we asked for a perpendicular vector, we got 0. Both are correct. And it kind of makes you wonder, doesn't it? If a rule as simple as multiplying something by itself can be this flexible, what other rules in math or even science aren't as set in stone as we think they are?